And we will get started. So here's your exam from last time. I'll work the solutions for you. All right, so if we have something like this, first thing we want to do is simplify both sides. We got x's showing up in 3 different places, right? There's no fractions, so that's guys. Let's get rid of these parentheses first. Okay, so this is equivalent to if I distributed this 3 across. We have a 3x and a 3 times 2 gives us a 6. And then we have a plus x. Now let's distribute this 2 here across. 2 times x and a 2 times 1. Okay, so those are equivalent. Now let's combine like terms. 3x and an x gives us 4x. And that's really all we can do as far as combining these two. Now we got x's in 2 spots. Let's get all the x's to the left. So we'll take and subtract 2x from both sides. So 4x minus 2x is 2x. Those go away like we planned. Okay. Now we still want to get the x by itself. We got a 2 and a 6 in the way. Let's get rid of this 6 first. Subtract 6 from both sides. So we get rid of that. That leaves us with just the 2x. And then 2 minus 6 is a minus 4. And that's groovy. Now we just got to get rid of the 2. So let's divide both sides by 2. Because 2 over 2 is just 1. So x here is negative 4 over 2. 4 over 2 is 2. And then we put a red box around our answer. Any questions about this? How comfortable are y'all with this stuff? Pretty okay? Y'all seen it before. Some of y'all are masters. Some are like, I just need a little more practice. Right? Okay. All right, here's one. And there's a bunch of fractions. Fractions suck, right? We could be like, let's get rid of parentheses, but let's get rid of these fractions first. Okay. What can we do to get rid of these fractions? If I multiply everything by 2, I'll get rid of that. If I multiply everything by 3, I'll get rid of those. So I kind of need to multiply everything to 2 and to 3, right? Or 6, right? If I multiply everything by 6, so I'm going to use shortcut notation here. I'm going to be like times 6, right? That's my cheater notation, right? So 6 times this thing, I have a 6 over 2, which is 3. Then times 3 would be 9. Here, 6 divided by 3 would be 2. 2, and then we have our x. Now for the other side, I have a 6 divided by 3 is 2. Then times that 2 would give me 4. All right. So let's just get rid of those fractions. Now that we got rid of the fractions, let's get rid of these parentheses. Okay. To distribute this 9. 9 times x is a 9x. And a 9 times 2 is 18. And I still got a 2x hanging out here. Now I'll distribute this 4. A 4 times an x is 4x. A 4 times a 1 is 4. Okay, now we have x's in 3 different locations. We can combine these like terms. Let's go ahead and do that. 9x and 2x is 11x. And I have an 18. And the other side, I can't do much with it yet. All right, so we want to get the x's all together. They're in 2 different spots. So let's subtract 4x from both sides. So that'll go away. So 11x minus 4x is 7x. And our 18, and on over here we still have a 4. Okay, we want to get the x by itself. We got to get rid of the 7 and the 18. It's quicker to get rid of the 18 first. So subtracting 18 from both sides, I'm left with 7x. See, 4 minus 18 is what, a negative 14? Yeah, all right. So now I got to get rid of the 7. We'll divide both sides by 7. I'm left with x equals -2 again. Same answer. So this says exactly the same thing this does. They're logically equivalent to both, saying just x is -2. I think I did it wrong. Whenever I did it the other day. Right after class, before I leave, I usually work the exam in here. Yeah, I got it totally wrong. I'm gonna have to re-upload this. Let's see what I did. Let's see what I did wrong when I did it in a hurry after the last class. I multiplied everything by 6. All right, 6 over 2 is 3 times 3 is 9. 6. Where?
On the 7x plus 18 equals 1.
Here?
Yeah, and then you did the minus 18 on the log.
Yeah, why do I have a 1 here?
If you did the second step, the 11x plus 18 equals 4x plus 1 to balance correct. But then you just switch the 1 and the 4.
I switched the 1 and the, yeah, right here. 4 times 1 is 4, right? That should have been a 4. That should have been a 4. This is good. That's okay, but this should have been a 4. Which would have left me with -12. No, -14, right? Divided by 7, and I should have got a -2. All right. So I'll have to I already uploaded this. So I'm gonna have to re-upload it again after class. So I won't forget to do that. So, I mean, it's easy to make mistakes, right? I've done this 100 million zillion times, and I still make mistakes if I do it too quickly. Right? That's why it's important to check your work, right? How do we check our work? You plug your x back in, right, to the original. So let's go ahead and do that. All right, I didn't check my work. I totally should have. So let's check at least number 2. The right-hand side, which is this, right? We're checking to see if -2 is the right answer. So if we replace x with a -2, what do we get? Let's see, this is 0. 0 times anything is 0. So this is just -2/3. Look at the left-hand side. Left-hand side, if we replace the x with a -2, we get 2/3 times -2 plus 1 is a -1, so that's -2/3. Those are equal, right? All right. So it's time for a quiz. Will be daily quiz number 4, number 1. And because this basic algebra stuff is so important, right, I'm going to give you some more of that, right? I could give you some business stuff. I don't remember what we covered last time. What did we do? Graphing? No. iParty, yeah. All right, what did we do last time? We did the quiz. Oh, solving inequalities. All right, I'll throw one in there that's an inequality. Yeah, we're just doing basic stuff. Yeah, we got to example 3, iParty. The hardest part of using these formulas like iParty is the algebra, right? Okay. So let's make one of these, make these inequalities here. So if I have, I don't know, I'll do a 3 and a 5. So 2/3 x minus 2 plus 3/5 x equals 3/7 x plus 2. No, that's one. I want to do an inequality. Do greater than or equal to. There's number 1. And 2, 4, 3, and 4 less than or equal to. 3/8 x minus 1. There we go. These are like the same stuff. I put more parentheses in there and more x's. So you're going to use the same tools, right? It's the same algorithm to knock this down, all right? Get rid of the fractions, get rid of the parentheses, collect like terms, and get your x by itself. Remember, with these inequalities, if you multiply or divide by a minus, then you have to switch the inequality. The inequality gets switched, right? Because 1 is less than 2, but minus 1 is bigger than minus 2. Remember that. So that you should be able to do this. We'll take 10 minutes at 3:21. I'll work this for you. In the meantime, feel free to work together, all right? If this is like even remotely challenging for you, feel free to work with somebody. Master it. Even if you know this stuff really well, it's good for you to show somebody else. You really don't know this stuff until you've taught it. And looking at what y'all wrote on your exam, some of y'all, you don't have an equal sign anywhere in your work, right? We're starting off with something equals something, right? It's a balance. It's saying this is equal to that, and it's asking when is this equal to that? When is this equal to that? For what values of x is the left-hand side equal to the right-hand side? This balance or scale is equivalent to this one, all right? So some of y'all didn't have any equal signs at all. Some of y'all are still getting used to this symbol, right? That's not the same thing as just this, right? There's extra little end caps on it, okay? So if I just put equal, equal, equal here, if I just have a whole bunch of equals, it's like, well, which side is the left-hand side? Which side is the right-hand side, right? What this is saying is that this equation is equivalent to this equation. So keep practicing, all right, with that symbol till you get it down, all right? It takes a while to get used to it, to know when to use it, because later on we will have like equal, 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 and then we'll have that. And then we'll have an equal, 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 right? And so you want to be able to see how to use chain equalities and how to say that equalities themselves are equal, all right, are equivalent. All right, so, but if you're doing your work and you don't have any equal signs at all, right, utilize that tutoring lab or take advantage of your classmates, right? Start doing the students who need the most help are the ones who need to be doing their work on the whiteboard. So the students who get their work done early can look up and help them out, right? But the students who need the most help are the last ones that want to do anything on the whiteboard, right? Same thing goes like if there's a word that you ever like don't know how to pronounce, right? Take your best guess and say it really loud and hope that somebody will correct you because that's how you learn, okay? That's called a growth mindset, right? Some people go through their lives without that growth mindset, so they never learn much. In fact, they don't want to be corrected. They'll take it personally and they'll attack anybody that ever tries to help them, right? Those are your rural rednecks that, just don't ever learn anything, right? It's like, I know plenty of 12-year-olds that are just as mentally and emotionally mature as most, 40 and 50-year-olds, and that's why. If you really think about it, grown-ups are nothing more than really old babies. Some people learn throughout their life. Some people avoid it because they're too scared or insecure, or they just feel like it's an attack whenever somebody tries to teach them something. So we have to overcome that, be open and, grow into some confidence, okay? So there's a few tips and tricks there for you for becoming successful, right? All right, first thing I look at this thing and I see fractions suck. How do I get rid of the fractions? Well, if I multiply everything by 3, this will go away, but it won't get rid of this fraction or that fraction. Same thing goes if I multiply by a 5 or a 7, right? Really, I need to multiply everything by a 3 and a 5 and a 7. 'Cause if you think about 3, 5, and 7, those are all prime numbers, right? So I would have to multiply everything by a 3 and a 5 and a 7. That would get rid of all the fractions. I don't know what 3 times 5 times 7 is. I don't need to know. What I do want to do is multiply. If I take and multiply this thing by that guy, right? I'm gonna have to multiply it by each of these 3 objects here. If I multiply this by this first thing, the 3 over the 3 will go away, and I'll end up with a 5 times 7 times 2. 5 times 7 is what, 35? Times 2 would be a 70. Does that make sense? Whatever this number is, times this number. Oh, and I multiplied by 2. So the 3 over the 3 would go away. I'd have a 5 times 7 times a 2, which is 70. Now let's look at this term. For that one, the 5 over the 5 would go away, and I'm going to be left with a 7 times 3 times 3. 7 times 3 is 21 times 3. 21 times 3 would be 63, right? So I'd end up with a 63x. Now for this guy, the 7 over 7 will go away, and I'm left with 3 times 5 times 3, or 9 times 5, which is 45. So we have big numbers now, but we don't have any fractions. Now understand the motivation for that? Fractions suck, let's get rid of them. How do I get rid of them? I need to get rid of the 3, the 5, and then the 7. So I'm multiplying everything by a 3 and a 5 and a 7, both sides of the equation. So each term, all right, is this term, and this term. Every term on each side has to get multiplied by the same thing in order to maintain logical equivalence. All right. So this is the same as this. I'm missing it. Now it's just a matter of simplifying. Let's get rid of these parentheses so we can collect like terms. 70 times x is 70x, and 70 times 2 is 140. 45 times x is 45x, and 45 times 2 is 90. Now let's collect our like terms. We got x's and x's. 70 and 63 is what, 133? Is that right? And then we still have this minus 140. 45x plus 90. Get this guy and put it on the next page. Okay, so now I got x's in 2 spots. So let's get all the x's to the left by getting rid of the x's on the right. Whatever I do to the right side, I have to do to the left. I'm getting rid of the x's on the right. What is 133 minus 45? I'm going to use my calculator so I don't screw it up. 133 minus 45, 88. So I have 88 x's minus 140 is greater than or equal to 90. So now I got to get rid of the 88 and the 140 to get the x by itself. It's easier to get rid of the 140 first, so we'll add 140 to both sides. That gets rid of that like we wanted. And then 90 and 140 is 230. Thank you. All right, so now we just got to get rid of this 88 since it's being multiplied. Divide both sides by 88. Okay. So this is equivalent to this. Now I'm going to throw in a chain equality. All right. I want to simplify this. I could say, okay, this is the same thing as x is greater than, and then simplify this, right? That's kind of how I've been doing it. Or we could say, we have this, let's simplify that. This guy is equal to what? We want to simplify, reduce this equation, right? So 230, I'm going to divide by 2. It's 2 times 115. 115 is divisible by 5, and then 23. So I just broke it down into its primes. 88 is 2 times 44. 44 is 2 times 22, which is 2 times 11. All right. So I know I can at least get rid of that 2, and well, that's it. All right. So now I'm going to multiply these back out. 5 times 23 is 115. 2 times 2 is 4, times 11 is 44. So this is equivalent to this. But what am I saying here? I'm saying x is greater than or equal to that, and that is equal to this. So in the end, I can reiterate, okay? So x is greater than or equal to this fraction, but this fraction is equal to that. So here's a thing where I have equal, equal, equal. So how do we read that, right? This would be called a chain equality. We're comparing the ends, right? Here's our work done. But at the end of the sentence, what we're looking at is the ends. X is greater than or equal to 115 over 44. So I go ahead and write that again just to be clear. Okay, if you're not comfortable with that, you don't have to use chain equalities. It's one thing we use to save space and write less, right? I'll say, or instead of doing it that way, from right here, I could have just said that is that, right? This is just showing the work that I did, right? To simplify that, okay? Yeah, if you gotta take off, you gotta take off, man. Okay. I know y'all are still getting used to this symbol in between equations, right? But sometimes we're going to want to do stuff like that, right? I have this. I want to simplify that. I don't want to rewrite it, right? So I'll just go ahead and simplify that. But at the end of this chain equality, what I'm comparing is this with that. So just do that. And that's the emphasis. So that's what I'm rewriting. Sometimes we do chain equalities like that. Now let's look at number 2. All right, now I have fractions again, and fractions suck. So how do we get rid of them? All right, the last approach I said, well, I would multiply everything by a 2 and a 4 and an 8, right? But the only reason I did the 3, the 5, and the 7 is because 3, 5, and 7 are all prime. Okay. This guy, I could just multiply everything by 8 because 4 divides into 8 evenly. 2 divides into 8 evenly, and 8 divides into 8 evenly. All right, so I don't have to multiply everything by a 2 and a 4 and an 8. Right? Just the 8 will do. Okay. So if you think about it, 4 is 2 times 2, and 8 is 2 times 2 times 2, right? So really, I'm multiplying everything by 2 3 times. Multiplying everything by 2 times 2 times 2. Because, well, the end result is to get rid of the fractions. We need something that divides evenly. Okay. So if I multiply everything by 8, we have to multiply it by that term, this term, and this term, each of the 3 terms here. So for the first one, 8 divided by 4 is 2, times 3 would give me a 6. Now for this one, 8 divided by 2 is 4. And then 8 divided by 8 is just 1. I'm left with that 3 there. That's your first step. Get rid of the fractions because we all hate fractions. Now we just use the distributive property to get rid of the parentheses. 6 times x is 6x. 6 times 3 is 18. Do the same thing here. A minus 4 times x is minus 4x. A minus 4 times 4 is a minus 16. A 3 times an x and a 3 times a minus 1. All right, now we have x's in 3 different locations. Let's combine these like terms. 6x minus 4x is 2x. Oh, and we can combine these as well. 18 minus 16 is 2. All right, so we have x's in 2 spots. Let's get them all to the left-hand side. So I could subtract 3x from both sides. So 2x minus 3x is a negative x. All right, let's get rid of this plus 2 by subtracting 2 from both sides. We have a negative x less than or equal to a negative 5. But we just want x, not negative x. So if we multiply everything, both sides by a minus 1, this inequality has to flop. It just flops, right? Multiply everything by minus 1. And put a box around it. You good with that? All right. Everybody should be getting hundreds on all the quizzes, right? Any questions? Don't need more time. Okay. So moving on, let's see, last time we did I par T, and by the time we got this problem number 8 with these fixed costs, I'm pretty sure we were all toast, right? So let's go ahead and rework this problem 8. What section are we in? In 1.1. So give me a second to load the book. 1.1 match problem 8. Had to do with what the break-even point. All right, so profit is revenue minus cost. Your break-even point is when your revenue and your costs are equal. Basically, if you build a manufacturing plant, that's a bunch of cost up front. As you start selling stuff, you start making a little bit of money, and eventually you made enough money to pay off that manufacturing plant. That's your break-even point. After that, you should be able to make actual profit. However, sometimes it can go the other way. Sometimes you want to, in that scenario, you want to sell enough to eventually make a real profit, right? Sometimes it's the other way around, where the cost gets more and more expensive instead of less and less. So you want to keep selling up to a point and then stop, because if you keep manufacturing after that, you'll end up just losing money. Okay. E-text. I know Pearson has an app, like I have one on the iPad or whatever, so you can download the book there. I don't think they let you like download the PDF where you can just use it. You have to like, download one page at a time every time you access it. Do you know if you can download the whole book? You can? They won't let me do it with Windows 7. Then you could just skip pages real quick. Oh, I have audio as well. Wow. That's cool. I'll have to check it out. Like, I have a really nice iPad, but see how I can like quickly take snapshots, I could just be like, I just want this and paste it. a real pain in the butt to do with the iPad. You have to like copy the thing and then you have to crop it and then you have to paste it and it's just real slow. But if I gain speed by being able to not have to do all of this, might end up being faster. I'll have to look into that again. And for some reason, this little scroll bar here never shows up. I don't need it. About the 50th time I click and drag, the scroll bar will show up. 1.1. So forget where we go for 1.1. The schedule they gave us just bounces around through the whole book. Chapter 1, chapter 13, chapter 4, then chapter 7. All right, we made it. We made it pretty far, huh? Let's see. Yeah, this is where we got burnout. Yeah, this stuff. This stuff you want to do at the beginning of class, but the mind is still fresh. All right, so what did we do? Mary paid 8.5% sales tax. So our tax rate is 0.085. Remember, you always get rid of the percent symbol, right? 8.5%. Remember, the percent symbol is just shortcut notation for writing over 100. When you divide by 100, you're moving the decimal to the left twice. So, and then there's $190 title and license fee. So I'll use like F for fee. All right. And she bought a new car for a total of this amount. So the amount is $28,400. What is the purchase price of the car? So I'll use P for the purchase price. What we have here is the amount is the licensing fee plus the purchase price plus the interest, not the interest, the tax. And the tax is the purchase price times the rate, the tax rate. All right, so I'm writing down an equation without any numbers in it yet. We could have wrote down all the numbers and there'd only be a P there, right? We know this number, we know that number, and we know that number. I could have written it down with the numbers. But then when you're solving for P, you're writing all those numbers over and over again. And let's say those numbers were $137,556,432.98. That's a whole lot of writing to write in each step, right? That's why it's good to just leave it as letters, solve it, and then in the last step, plug the numbers in, right? When it's simple and small numbers, it's like you want to put the numbers in first, but I want you to understand the process, right? Does that make sense? You have the fee, the price, and the tax. So we need to find out what P is. Okay, well, P is showing up two places here. So we could rewrite this. Well, one thing we could do is we could get this F out of the way. So if we subtract F from both sides, we're going to get an A minus F is equal to, we got this. So what we're going to do with this is we're going to factor out the P. This is P times 1 plus R. Now see that? P plus PR, right? P is really P times 1, right? So you have a P times a 1 and a P times an R. This is P times 1 plus R. Sometimes things like this mess with y'all because there isn't a number here. There's always a 1 present, right? We just don't write it because that looks goofy. So if I write it like this, you can see that it's that, right? But without there, you might not know what to do, okay? So always remember, anything is always itself times 1. So we're just factoring the P out. That way now there's 1 P instead of 2. At this point, we want P by itself. So we'll divide both sides by 1 plus R. So we're left with P equals A minus F over 1 plus R. And now we plug in our numbers. A is 28,400. F is 190. And on the bottom, we have 1 plus 0.085. Now I wrote the units here, dollars, right? Dollars minus dollars is dollars, and we're dividing by a pure number. We're going to be left with simply dollars, right? So this we can plug into our calculator. 28,400 minus 190 divided by 1.085, and we get exactly $26,000. And then we put a box around our answer. So see how concise that is? We did the minimal amount of writing, right? The goal in math is to be precise and concise. Makes a lot more sense at the beginning of class than at the end of class, doesn't it? All right, let's look at our next example. Let's see. Break-even analysis. Okay. I think this is where we burned out right here, actually. All right, so break-even analysis. This has to do with profit being revenue minus cost. So you have your cost, right? You start selling stuff and you start making money. That's your revenue, but the profit is the difference between your revenue and your cost. So the break-even point happens when your profit is 0. When your profit is 0, when the revenue is equal to the cost. So let's see, fixed costs are $48,000. What are they doing? A manufacturing company makes bike computers. So they have to build their manufacturing plant. Okay, so we need a letter for fixed costs. I'll use F here. F for fixed cost, 48,000. I'm going to leave the dollars off because we know we're working in dollars, right? If we're doing anything else where there's lots of different units like pounds and links and stuff, then you want to write your units. But here things are so simple. We know it's all dollars, right? So fixed costs of 48,000. The variable costs are $12.40 per computer. So I'll use V to be $12.40. So our total cost is the fixed cost plus the variable cost. All right, which is 48,000 for the fixed cost. Now the variable cost isn't just this, right? It's $12.40 per computer, right? The variable cost is $12.40 per computer. We need a variable for the number of computers, right? In the end, it's going to say, what are they saying? How many bike computers must be manufactured? So we're going to let X be the number of bike computers. So when we solve, we're going to solve for X, right? The hardest part of word problems is labeling things. Like, what do we define our variable to be? Look at the end question. Whatever the last question is, whatever it is they want you to find out, that's X, right? So it's going to be $12.40 times X, the number of computers. So in this case, I'm going to go ahead and throw these dollar signs in here. All right, so it's right, $12.40 per computer, and then X is computers. X has units of computers. So as you see, the computers cancel out and we're left with dollars. All right, does that make sense? If X is computers and V here, our variable cost is $12.40 per computer, you need to multiply that times computers to get computers out of there, because in the end, you want your answer to be in dollars. You don't want it to be dollars computers or anything like that. Or in this case, you want computers. The answer is going to be computers, the units. They're not asking you how much do we charge They're asking us how many byte computers. X has units of computers. When they put like square brackets around something, they're saying what are the units of this variable, right? If it's a length, it would be like feet or something, right? So X here is units of computers, right? They just kind of shuffle all that under the rug when they're doing their example here. But here's our cost: 48,000 for the plant, and then $12.40 times the number of computers. So there's our cost. We want to set revenue equal to cost, so we need an expression for revenue. Well, they say we're selling the computers for $17.40 each. So the revenue is $17.40 times the number of computers. That's how much money we get. So here's our cost. Here's our revenue. When are these dudes equal, right? Remember, when they're equal, that's when the profit is finally zero. It's when you finally paid off that manufacturing plant. So the revenue is equal to cost whenever 48,000 plus 1240x is equal to 1740x. Okay. Really, there's dollar signs here everywhere, right? But the first thing I'm going to do is divide everything by dollar sign. So we can just throw the dollar signs away. They fall out of the equation. We're going to be left with computers, basically. All right, so this is something simple. Y'all know how to solve this. We have to get our x's together. Since this is bigger than this, let's go ahead and get x on the right. I know y'all like to put x on the left, x equals this, but you know, 2 equals x is the same thing as x equals 2. All right, so I'm going to subtract 1240 from both sides. No, yeah, 1240x from both sides. So I'm just left with 4,800, 48,000. 17 minus 12 is 5. So now divide both sides by 5. And at this point, I'm just going to write x on the left because I like it better on the left. So 48,000 divided by 5 is, if it was divided by 10, it would be 4,800. So it's 5, so it'd be twice that. It should be 9,600. 9,600 computers, right? X is in units of computers, right? Because this is really 1240 per computer, and this is X computers, right? So X has units of computers like we wanted it to have, because that's what the question's asking. How many computers? All right, any questions? Right, the business part is easy, right? The revenue has to equal the cost for the profit to be equal. That's your break-even point. Let me do a match problem. How many byte computers would a company have to make and sell to break even if the fixed costs are 36,000 and variable costs are 1040 per computer? All right. So let's just write down our cost function. Our cost is the 36,000 for the manufacturing plant, and then $10.40 times the number of computers that we make. And again, these examples, we're assuming that we sell every one of them that we make, right? In the real world, that doesn't ever happen, right? Like later on in the class, we'll look at examples of how things change, how prices change based on demand and all that. We do a lot of that in calculus, business calculus. So there's our costs. Our revenue, if we're selling them for 1520 each, our revenue is 1520 times the number we sell. And again, our profit is revenue minus cost is 0 if and only if revenue is equal to cost. All right. I mean, we could write it this way. We don't have to set them equal. We could use this. We could say, okay, here's revenue. minus cost has to equal 0. It's the same thing as setting them equal to one another. Setting R equal to C is the same thing as saying R minus C equals 0. Right? It's the same thing. So here, though, if we do it this way, we have to distribute this minus sign. So that becomes negative, and this becomes negative if we're going to get rid of those parentheses. Right? So having that over there is the same thing as putting it over here, but making it all positive. Right? Whatever. The same thing. So we have 1520 minus 1040. What is that? That's 4.2 and another 0.6, 4.8. Is that right? 1520 minus 1040. 4.2 and yeah. And then we have minus 36,000 equals 0. All right. So let's get rid of the 36,000 by adding it to both sides. We have a 4.8x equals 36,000. Now I want the x by itself, so let's get rid of this 4.8. Boom. And I don't know what that is off the top of my head. So we'll use our handy duty calculator. 36,000 divided by 4.8. And we get an exact whole number. Right? If we got like a decimal or something, we'd have to round because we can't manufacture and sell 3/4 of a computer, right? It has to be a whole number. So you'd have to round up, not down. That makes sense? Okay. Number 10. Do they want us to use this chart here, maybe? Let's see. We'll grab the chart while we're at it. I wish they had something on the iPad that I could just snap a piece of the screen and paste instead of having to snap the whole screen and then crop that and then paste it, as much as I do this, right? All right, the Consumer Price Index, or CPI, is a measure of the average change in prices over time from a designated reference period, which equals 100. Okay, CPI. So the difference, the change in prices from 82 to 84 is equal to 100. That's the CPI. They're fixated on 100 here. And they're looking at the average change in prices. Okay. The index is based on prices of basic consumer goods and services. Table 2 lists the CPI for several years from 1960 to 2016. I'm missing part of the chart here. Oh, there we go. That makes more sense now. Yeah, need the whole chart, right? I've never heard of CPI, Computer Price Index, so we're gonna have to think about this a little bit. Like, what does this mean? So they're giving us the CPI for these years here. What does that mean? Let's see. A measure of the average change in prices over time from a designated reference period, which equals 100. I don't know about y'all, but that's a very awkward sentence. I'm not making much sense of that. Like, I'm a math major, I'm not a business major, right? So I don't know, maybe we could figure it out what that means. All right, if we read the rest of the problem. Oh, here we go. The index is based on prices. Okay, we read that. Table 2 gives us CPI for several years. What net annual salary in 2016 would have the same purchasing power as a net annual salary of 13,000 in 1960? So if you have 13,000 bucks in 1960, what is that equivalent in 2016? All right. So in 1960, we have an index of 29.6, but we want to relate that to 2016 with our CPI of 241.7. All right, compute the answer to the nearest dollar. I'm gonna have to look at their solution. I don't know what that means. I have no idea. I've never seen this before in my life. The other class I taught, which is the same thing, the same title as this one, but it wasn't didn't come with the COREC, right? So it was real short. They didn't have this in there. So let's look at the solution, see if we can make sense of what they're talking about here. I mean, that's a thing you always want to ask, like somebody says they made so much money at a certain time. It's like, well, what is that today, right? So this is how they do it with the CPI thing. Let's see if we make sense of their solution here. By the way, next semester when I teach this, I can be like, oh yeah, this is easy. Blah, 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 blah. All right. Here we go. Let's see. So we're going to let X be the purchasing power of annual salary in 2016. Why would we do that? They say compute what net salary in 2016. So X is going to be the salary in 2016, right? That's what the question is. So that's what we want to define our variable to be. X is the salary in 2016. That's equivalent to 13,000 in 1960. So it's the purchasing power of an annual salary in 2016. How they state this here. All right. So what can $13,000 from 1960 buy you in 2016? Right. So it's equivalent. So we know this from the chart. Here's our CPI in 1960. Here's our CPI from 2016. All right, what do we need to do with this? The ratio of a salary in 2016 to a salary in 1960 is the same as the ratio of the CPI. Okay, so we could do, let's see, salary. I'm going to do salary for 1960. Compare that to the salary in 2016 is the same thing as the CPI. Again, in 2016 compared to the CPI in 1960. So those ratios should be equal. The ratio of some amount of money in 2016 compared to 13,000 in 1960, the CPI ratio should be the same. Okay, so that's how we utilize that. So here we set it up. So X is our 2016 equivalent of 13,000. Here's our CPI for 2016 versus our CPI of 1960. All right, so this is our setup. So first we need to define our variable. We know what the variable is from the question itself. It tells us what to label our variable. Then we look and set up a simple ratio. Okay. From there, we just solve for X. We do that by multiplying by both sides by 13,000. Right. So if I multiply this by 13,000, right? Multiply everything by 13,000. So on this side, it just goes away. But on this side, we have to keep the 13,000. We simply multiply. We have 106,152. I understand the math. The math is real simple, right? It's just the definition of what CPI is. But kind of technically, as long as we know how to do it, we don't even need to know, like, where the hell do they get these numbers, right? Well, we don't need to know how to figure these numbers out. They're just given to us in the chart. So we just need to know how to utilize them, right? So over here, if we had salaries, equivalent salaries, the ratio of this to this would be the ratio of this to this, whatever those salaries are. If we had a salary, actual salary column, which we could actually conduct now, right? everything would be based off of $13,000, right? Oh, we did this. Let's fill in the chart so we know how to do this one. So if I put salary, if I put 13,000 right here for starters, so I'm comparing everything to 13,000. We found that for 2016, the 106,152. Right, so those are equivalent, okay? We could fill in the others. If I wanted to do, say, let's do 1999 here. So X is the money from 1999 compared to the 13,000 from 1960. That's the same thing as, let's see, 1990 says 156.9 compared to 29.6. Those ratios should hold. So to get X, we just multiply both sides by 13,000. Which would give us 156.9 times 13,000 divided by 29.6. So I'm getting $68,908. Right, so I could fill in all this whole chart based on $13,000 in 1960, right? But we could change that. We could be like, well, what if you made $100,000 in 1960, right? What would that be worth in 2016? So you can use this the data in this chart to figure that out for any salary, right? It's not good just for 13,000. I could pick any salary at any time and compare it to another time. So what if I made, put salary here. Boop, 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 boop. What if I made $100,000 in 1973? How much should that buy you in 1999? All right, well, I'm going to call this X. So 1999 money compared to 1973 money, I need to compare the CPI. The CPI for 1999 is 156.9 compared to 44.4. Those ratios should hold. So to figure that out, I just multiply both sides by 100,000, and we would get 156.9 times 100,000 divided by 44.4 gives me $353,378. So $100,000 from 1973 is equivalent to $350,000 in 1999. I wish we had like more recent data from like today, from like just 6 months ago, right? Prices keep going up. Like a big bottle of apple juice that was $2.50 is now like $6, just from like a couple of months. Went to HEB yesterday, it's $350. Christ, it's just like half a basket of stuff. Meanwhile, our wages aren't going up, but the filthy, filthy rich, they're just banking big, right? This whole inflation thing is a scam. The big companies, they're just making record profits every quarter, more money than they've ever made. We're not making any more money. Our prices are going up. None of them pay any taxes. We pay a lot of taxes. I pay a lot of taxes. All right, so we're not doing match column number 10 because actually that is the one they did. When that, if you made $100,000, oh, they're going the other way around. What's if you made $100,000 in 2016? What would that be in 1973? I just picked $100,000 for 1973 randomly. I almost read their mind. All right, but yeah, you can go the other way around. Like in the same way. It's the same, you just set up a simple ratio. So now we know how to use the CPI ratio. I still don't know where they get these numbers though. I didn't understand their thing. About parts per 100 or something. But I'd have to look at it in more detail to figure out what those numbers actually represent. And we're done with 1.1. So from here, I have no idea where we're supposed to go. Let's look at files and just rough schedule regulation. Let's, we could take a bathroom break. Let's do that while I take a 5-minute break while I figure out what we need to learn next. Okay. All right, so 1.2 where we're at, section 1.2. So the very beginning of the book has this long paragraph with all this vocabulary. So you can read that if you want. We're just going to jump in. And then here's a picture with all the vocabulary, right? Like when you have an ordered pair. So if you have a plane, we like to call this X and we like to call that Y. We could call it anything we want. Here's your real number line. Here's a real number line. You could pick any point you want. This is X comma Y. So the first number is how far you go left or right. The second number is how far you go up or down. These numbers have names, the abscissa and the ordinate. I'll never remember that, but all these things have names. You can see there's 4 quadrants. We call this quadrant 1, and for some reason we go counterclockwise. So this is 2, 3, and 4. It's nice to label the quadrants so we can talk about them. Like, it's over there in quadrant 3 or whatever. Okay. So over here, if you've gone to the right and up, so in this quadrant, since you've gone to the right, your X is positive, and since you've gone up, your Y value is positive, right? If you're down here in quadrant 4, we've gone to the right, so the X is positive, but since we've gone down, the Y is negative. We're in quadrant 2, we've gone to the left, and we've gone up. In quadrant 3, we've gone to the left, and we've gone down. So this is basically this quadrant is the same as the other quadrants, except you might have to change one of the numbers to be negative, all right? So most of the math happens in quadrant 1 because the other quadrants look just like it, but when we start graphing things are a bit more technical, okay? So what we really want to be able to do here is graph stuff. We want to be able to graph functions. All right, so when they give us an equation that has not just X, but a Y, right? If there's 2 variables, when we solve this, we don't just end up with X equals 2 or X equals 3, all right? If we have 2 variables, I have to give you 2 numbers for an answer, right? So if I have like 2X plus 2Y equals 2, when is this true? Well, I have to give you a pair, an X and a Y. So if there's 2 variables, the solution is going to have an ordered pair. There's going to be an X and there's going to be a Y. I would write it like this: X equals something and Y equals something. Let's see, in this case, they both have to be a half, right? If X was 1/2, 2 times a half is 1. If Y was 1/2, 2 times a half is 1. 1 plus 1 is 2. So I could say X is a half and Y is a half, right? If I plug that in for X and that for Y, it would be equal. Well, we would write this as 1/2, 1/2. But that's not the only solution, right? When we do something like this, X plus 1 equals 0, there's only one answer. X has to be minus 1. That's the only thing that satisfies that equation, right? This equation, I just found out that's a solution, but the problem is there's an infinite number of them. There's an infinite number of X's and Y's that I could plug in that would satisfy that equality. All right. So if I had something like this, for example, I could rearrange it. See, in this way, it looks like this. They say if there's an x and a y, there's no x squared or y squared or anything. You can always rearrange the equation to make it fit that form. This fits that form, right? It's something times x, something times y, and then the number that doesn't have x's or y's. I can always shuffle things around to make it look like that. I could also take this and I could divide everything by 2. And then I could get the y by itself and write it like that. So this equation is the same thing as writing that equation. All right, I could shuffle it around, but they're saying exactly the same thing. Okay. And what we like to do is we like to call y f of x. And we like to treat this side as a function, right? And then we graph this. So basically, since this thing has an infinite number of solutions, if I tried to graph them all, right? So a solution is an ordered pair. If I took all the possible solutions to this equation and I graphed them, it would look like this. This line right here. If I pick any point on this line, like let's say this point right here is what, 1, 0, right? If I plugged in a 1 and a 0, 2 times 1 is 2 plus 0 is 2. So 1, 0 is also a solution to this thing, right? X equals 1, y equals 0. That's a solution. This is a solution. Both of these are solutions to this. There's an infinite number of them. And if I found them all and I plotted every one of them, they would happen to lie in a line, a straight line here. That blue line. How do I know it even looks like that? How did I just look at this and draw this line? Well, it helps if you rearrange it and write it like that. So later on, we're going to see that this is the slope. The slope is -1. That means the line is going diagonally like that. And this 1 here tells me that it goes through this point right here. So that's kind of the goal of the next several sections, is to be able to look at this, rearrange it to that, and visualize this. Right? This line is the solutions to that equation. All right, so we had equations for a long time before we figured this out. We figured out that, oh, you could just visualize this, right? So this is real convenient for people that like pictures instead of math, right? Oh, that's the goal. All right, so this is what we would call a linear equation in 2 variables. There's 2 variables, an x and a y, okay? And it's an equation. And if you graphed all the answers, all the solutions to this, they happen to be in a straight line. That's why it's called linear. Okay. If there was an x squared or a y squared or an x cubed or y cubed or anything other than x to the first power, it wouldn't be a straight line anymore. Okay. Y'all seen this before, right? Y'all graphed kinda, maybe a long time ago. Okay. So here's some theorems. Blah, 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 blah. We don't need theorems. Right, or business majors, not mathematicians. You don't need to prove theorems. Let's try to get these concepts down. Look at an example with a nice picture. So here's an equation. There's 2 variables, at x and a y. Okay. They say find and plot the y-intercept, the x-intercept, and check a point. What are they talking about here? Well, if I find all the solutions, here's their graph. They're going to show us the solutions. Any point on this line is going to be a solution to that. So like, look at this one right here, 8, 3. If I plug in an 8 here and a 3 there, let's see, 8 times 3 is 24. 4 times 3 is 12. 24 minus 12 is 12, right? So 8, 3 is a solution, okay? If I look at 4, 0, if I replace x with 4 and y with 0, let's see, 3 times 4 is 12, 4 times 0 is 0, 12 minus 0 is 12. So that number is a solution, that ordered pair, right? Again, there's an X and a Y, so the answer to the question, when is this equal to that? I have to give you two numbers. And there happens to be an infinite number of answers. And if I plot every single one, they happen to be on this line. All right, I'm not telling you how we figured out that line yet. We're just going to use their line. They're giving us the answers, and I'm just showing that those are the answers. All right. This is called the x-axis. This is called the y-axis. Together, they form what they call a rectangular coordinate system. Right, the x's and the y's are coordinates. How far you go left and right and up and down. They're rectangular because if I pick a point here, like if I pick this point, it's kind of making a rectangle. Okay, that's why they say rectangular coordinate system. Okay, we could keep checking every single point on this line, and I guarantee you they're all going to satisfy this equation. Okay, this point right here, where our answers cross the x-axis, that's called the x-intercept. And this point right here, where our answer line crosses the y-axis, that's called the y-intercept. Those are important answers. Again, there's an infinite number of them, but these two are kind of special. Okay, what's so special about them? Notice if you are on the x-axis, your y-coordinate is 0. If you're on the x-axis, it means you haven't gone up or down. So your y-coordinate is 0. If you're on the y-axis, you haven't gone right or left. So that means your x-coordinate is 0. Right? Those two solutions are usually pretty easy to find. Just think about it. If I let x be 0, I can just look at that. If I let x be 0, I can look at that and go, okay, y would have to be, right? Just divide both sides by a -4. What's 12 divided by a -4? -3, right? So let's say I'm trying to figure out what my answers are, right? I could just look at this with my brain and go, if I let that be 0, meaning I'm on the y-axis, if my x is 0, that puts me here. What's my y value? The y would have to be -3. So I could just be like, okay, 1, 2, 3. That point, that's one solution. And then I could be like, 2 points make a line, right? So if I let y be 0, that means I'm here, right? If y is 0, I haven't gone up or down. And I can look at this and say, okay, what's x? Well, 12 divided by 3 is 4. So when y is 0, the x is 1, 2, 3, 4. Right? 4. So this point here is 0 minus 3. This point here is 4, 0. Now that I have 2 points, boom, there's all my answers. Every single point on that line is a solution. So if I can just figure out 2 solutions to this equation, I can draw the line. And that line represents all the solutions. Now trying to figure out what's that point, I don't know. What's this point? I don't know. I can kind of, we'll figure out how to figure out other points on that line, all right? But this line is the representation of all the solutions to this equation. So you can see how quick and easy it is to figure out the x-intercept and the y-intercept. You just let one of the variables be 0 and see what the other one is equal to. We like those, the x-intercept and the y-intercept. It's quick and easy to find what they are, okay? Let's look at a matched problem here. And the concept is pretty simple, but there's a lot of subtleties, right? Let's look at this, all right? I want to graph this thing. So I want to just quickly give you a graph, a visual representation of all the solutions. If I let x be 0, I let x be 0, then I have -3y equals 12, right? And that would tell me that y has to be 12 divided by -3 is a -4. So that tells me, so 0 minus 4 is a solution. So let's graph this. 0, my x value is 0, so I don't go right or left. My y value is -4, so I go down 1, 2, 3, 4. That point right there, 0, -4. That's one of the solutions. I'll do it in blue. Now, let's let y equal 0. If I let y be 0, then 4x equals 12. Therefore, what's x? X is 12 divided by 4 is 3. So this is like a half of the equivalence. And that's fine. I'll just use that. It means implies. This equals that, therefore this equals that. Okay. So that means if x is 3 and y is 0, that's a solution. And if I graph this, x is 3, 1, 2, 3. The y value is 0, so I don't go up or down. So boom, right there, that's 3, 0. These 2 points are solutions. All right. And since this thing is linear, here's all the other solutions. I might be able to eyeball this. It looks like this point here would be 2 minus 1, right? I've gone over 2 and down 1, right? But my drawing might be kind of crappy. Maybe that's not an answer. Maybe it's just a crappy drawing, right? So this is called the intercept method. Intercept method. Where you look at the equation, let each variable be 0, figure out the corresponding x or y, then you know the x and y intercepts. You got 2 points make a line, draw a line to them. Called the intercept method. Later on, we're going to have the slope intercept method. Okay. So this is nice because it lets me draw the line, but it makes it kind of hard for me to figure out what are any of these other points. Right? Again, my drawing is crap. Right? If I drew it on a computer, like had the software graph it for me, well, I could just make the software tell me. It'll let you drag like an X down the line and it'll tell you the exact like point, right? But the thing is there's an infinite number of answers to this question. Each answer has to have an X and a Y, right? Because there's 2 things here, an X and a Y. So an answer has to have an X and a Y. And there's an infinite number of these ordered pairs, they call them. And if you drew every one of them, they would all line up in this nice little line. Okay. Now, using a graphing calculator, all right, your graphing calculator, you could just type into Google, graph this, and it would graph it. Okay. All right, we're not going to do graphing on a graphing calculator. Let's look at example number 3. All right, what do they mean by graph x equals -4? I'd be like, okay, here's my number line. Here's 0, 1, 2, 3, 4, -4. There. I graphed x equals -4. It's just a dot, right? Okay, what they mean here, though, is if you treat this as an equation with 2 variables, x and y, where they just didn't mention y, what they want here is this. So like, here's 1, here's 2, here's -1, here's -2. So this point right here would be -4, 0. Right? This point up here would be -4, 2. -3. This point right here would be -4, -3. This vertical line, every point on it has an x value of -4. Right? The y value is anything you want. You can go all the way up to infinity and all the way down to the -infinity. So if they say graph something and there's only an x, what they mean is they really mean is x equals -4 plus 0y. If there's 0y, you don't even write it, right? So treat it like there is a second variable, but it's just not being mentioned, meaning y can be anything you want. If you have 0 y's, you can let 0y be any number you want, but x has to be -4. So this vertical line here is x equals -4. Now, what about y equals 6? All right, treat it like there's an x in there, like there's 0x plus 0x. What they want you to do is they want you to have an x and a y. So the line where y equals 6, 1, 2, 3, 4, 5, 6. Here's y equals 6. That's going to be a horizontal line. Every single point on this line has a y value of 6, right? Gone up 6. So like this is 0, 6. I haven't gone left or right, but I've gone up 6. 1, 2, 3. This point here is 3, 6. I've gone to the right 3 and I've gone up 6. Right? The point is every single point on this line, the y value is 6, and x can be any number you want, right? You go over here, x has a different value. Over here, x has a different value. Here, x has a different value, right? Every point there, x has a different value, but y is always 6. So that's how you get a vertical line or a horizontal line. You just don't mention one of the other variables. Does that make sense? So these are like special cases. If there's an x and a y, it's going to be a line like this or this or this. It's going to be something kind of slanted, right? But because of symmetry, when you get to a horizontal line, the x's are gone. X can be any number you want. Vertical line, y value can be anything you want. Okay? So those are special cases there. Write the equations of the vertical and horizontal lines. Let's look at part B here. What do they want? So part B, write the equations of the vertical and horizontal lines that pass through the point 7, -5. Okay, let's look at that point. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So here's the point 7, -5. They want the vertical and horizontal lines that pass through that point. They want the equation for this line. Well, the equation for that line, every single point on that line has an x value of 7. The y value is anything you want. You can go up as far as you want or down as far as you want, but that vertical line there is just x equals 7. This line, the horizontal line going through that point, we've gone down 5. No matter what x is, no matter how far to the right or left we go, we are going down 5. So the horizontal line is just y equals -5. The vertical line is just x equals 7. The x and the y values from the point they gave us. Does that make sense? Kind of? All right. Slope. Right? The idea of slope makes sense, right? If you go up on a mountain, right? You're either going uphill or you're going downhill. All right. Slope. A positive slope means uphill. A negative slope would mean downhill. All right. Well, we're used to like degrees, right? We know what 45 degrees is and such, right? I mean, what is degrees anyways? Why is there 360 degrees in a circle? Why? Why isn't there 100? Right? Because King so-and-so once said there's 360. Maybe it has to do with there's roughly 360 days in a year. This goes back to, we use base 10, but other civilizations before us used different bases. Base 60 was a very popular one, hence 60 minutes and 60 seconds. The reason why they used 60 was because there's lots of numbers that evenly divide into 60. For doing arithmetic, it was more useful, but they didn't have a decimal system like we do. Right? So the slope of a line, they use m to denote the slope. That's the standard letter, M. And what it is it's your change in your rise over your change in your run. They say rise over run, rise over run, rise over run. Your vertical change divided by your horizontal change. Okay. And so they'll say, well, that's the difference in the y values over the difference in the x values. So let's look at a picture and see why that would make any sense. All right, it has to do with a triangle. Okay. So here's 2 points on the line. All right. We want to figure out what the slope is. Okay. Well, we're going from here up to here, right? So we go up that much, and then we go to the right that much. All right. So I'll call this like K and L. Okay. The ratio of K over L, the ratio of the rise to the run, that's the same thing as if I pick this point and this point. If I call this little L and this little K, all right? All right, so the ratio of this to this is the same as the ratio of this to this. It's the same as the ratio of this to this, right? If you have a triangle, or let's see, triangle or a triangle, these are all similar triangles. They're the same triangle, just bigger or smaller, right? The angles don't change. The ratio of this side to this side is the same as the ratio of this side to this side, which is the same as the ratio of this side to this side. That ratio is the same for all those triangles because those are the same triangles. They're just bigger or smaller. Okay. Let's get rid of all this stuff. So what we want though is we want uphill to give us a positive slope. We want downhill to give us a negative slope. Okay. So we also want a slope that's 45 degrees. If this is 45 degrees, what we want is a slope of 1. Okay. Straight up should be a slope of infinity. Okay. So that's how we do it. So in order to figure that out, well, these are our coordinates. To figure out what this is, what is this distance, we need to look at the difference in our y values, right? So we need to look at the difference in the y values. That's going to give us this actual length, okay? And if we want this distance, well, that's the change in our x values. That's why our slope is the change in the y's over the change in the x's. It doesn't matter which one you call x1 or x2. Like I could have called this 0.2 and called this 0.1. It wouldn't have mattered, okay? Because this is the same as y1 minus y2 over x1 minus x2. Right? If you switch the top and the bottom, you're getting a minus on the top and the bottom, and a minus over a minus, they cancel out, right? So it doesn't matter which one you call 0.1 and 0.2. But this is how you get your slope. Okay, so if you think about it, like this line right here, okay, what's the slope? Well, if I go up 2, I'm going to the right 2, right? So 45-degree angle, the slope is 2 over 2, which is 1, okay? If I have a 45-degree angle downward, that's a slope of minus 1, right? So if I go to the right 2, I'm going down to the ratio of the change in y over the change in x is minus 1. So 45 degrees is a slope of 1. Down 45 degrees is a slope of minus 1. And we want to have uphill and downhill. Okay. And now the issue is, I said you want a straight line like that, you'd want that to be a slope of infinity, right? Because you're going straight up. But the thing is a straight line also goes straight down. So is this thing, does it have a slope of positive infinity or negative infinity? Both. And that means it's undefined. So the slope concept works great for everything except for a vertical line. Horizontal line has a slope of 0. Okay. So let's look at that. Let's say I have this horizontal line, right? I'm not going up at all, right? So my change in y is 0, and then pick any number x, right? Right. So yeah, a flat line, that's a slope of 0. So it's a real convenient measure, right? And it's based on simply ratios of 2 out of 3 sides of a triangle. All right. I guess I'm running out of time. Sucks. So all right, let's do our daily. I keep going, but I don't think y'all can absorb much more, right? I quit. Today, my daughter had this little plastic horse and this little plastic pig. We held them close together. She goes, oh, they're friends. And then she says, so cute. And then she kissed each one. And then she just chunked them over her shoulder against the wall behind her. 2-year-olds are awesome. Huh? I did the exam from last time, the one I gave you at the end of the last class. So that would be exam number 3. Then we did quiz number 4, and now I'm giving you the exam number 4. All right, so can y'all handle a graphing problem yet? Probably not. I'll give y'all graphing next time, because I need to show you details. Like when you graph something, you don't want just to scribble like I did. Like you need to label certain things and all that. So let's do some more solve for x. Solve for x. All right, let's see here. 3 have x plus 4 minus 1/3 x minus 2. We'll do an inequality greater than or equal to 6. Yeah. 1, 6 x plus 3. And then okay, I know. I'll do a 2/3 3x plus 4 minus 5, 6, 2x plus 1 greater than or equal to negative x plus 1. Yeah, that's good. So be careful here. Like if you try to get rid of your fractions, I recommend multiplying everything by 6. So you'd multiply this by 6, this, and each of those by 6, right? Each term. All right. Technically we still have 15 minutes, so sneak out. I'll get in trouble for y'all letting y'all out early. All right, can you handle that? All right, get your work in by midnight. Do your My Math Lab homework. Don't fall behind on that. It's easy to fall behind. Remember, you have that tutoring lab. Take advantage of it.